these preview activities, and you, at first glance, you just look at them and they seem that they're fairly straightforward to answer, which is great. There's a lot going on in terms of previewing what's about to come up both today and the rest of the semester. I just want to point out that in terms of where we are today, class 11, the topic of today is basic functions and their graphs. And if you notice that everything you see after that is, even though if it doesn't even have like linear regression if it doesn't have functions in the title, everything for the rest of this course is going to deal with the concept of functions. So really understanding what makes a function and what doesn't make something a function is critical to the entire rest of the course. So that's where we're going to begin with today's work. So the very first question is, without giving you sort of the definition about functions or what makes something a function, it just asks you a question. You're given two sets. How do you know that these are sets, other than the fact that it says set 1 and set 2? What indicates to you that they're sets? Yep, Ian? The curly braces? Yeah. Okay, so these curly braces right here is what you want to do to indicate a set, unless you're talking about interval notation, which always represents sets of numbers, okay? So remember, anytime you're asked throughout the rest of this course to discuss a set, you have to use those parentheses. In set 1, how many elements belong to set 1? How many elements? 2. So set 1 has 2 elements. And remember, your individual elements are always separated with commas. So when you write a set and you have more than one element, you use a comma between your individual elements. Okay. And these elements happen to be of the form of an ordered pair that we typically would write like this. So set 1 and set 2 has 2 elements. Both of them are ordered pairs. Okay, so the question says, in which set is each x coordinate paired with only one y coordinate? So I looked around, and what did you have on your papers for that? Set 1, okay? I think everybody got the answer to that correctly. Yeah, Victor? Yep, that's great. Thanks for asking. In which set is each x coordinate? Well, in set 2, there's only one x coordinate, and that's 5. It is not paired with only one y coordinate, because in set 2, 5 is paired with the number 1, and 5 is paired with the number 2. So it's paired with 2 different y coordinates. That's what the language means. Now, visually, don't forget we have our visual mind to look at this. If you look at set 1 and we just quickly put like a little x and y axis here, and we like just plot the point 1, 5, we're just going to estimate there's 1, 5, and 2, 5 sits right beside it. Right? So you can see here that we have 2 different x values, and it is each x value is paired with one and only one y value. It happens to be the same y value. There's no rule saying it can't be the same y value, but 1 clearly knows its identity. 1 knows it's 5. 2 happens to have the same identity, 5. But you can see there's total identity confusion happening in set 2. Let's look at set 2. Set 2 says if I'm 5, if x is 5, I don't know if I'm 1 or if I'm 2. I have no idea who I am. So there's confusion going on with set 2. So the language is important. The x coordinate is paired with one and only one y coordinate in set 1, but 2 different y coordinates in set 2. And thank you for asking, Vic. Okay. You all were able to fill in the table for these 2 graphs, y1 and y2. It's important in this particular class, in any class really, but that you always label each graph with its equation. So your next project, you'll be doing a lot of graphing. You should always label every graph with its equation, because that's telling me all the information I need to know about that picture when I see the equation. If you have line segments, please extend the line segments with little arrows on the end of your lines, because these lines extend in both directions to infinity and negative infinity, and that's going to be important with some of the ideas we look at in a few minutes. So what else can you tell me about these lines based on your knowledge of linear equations when you look at them? Yep, Eric? They're parallel. And how do you know they're parallel without even drawing them, Eric?
They share the same slope.
Right, right. No, the slope is not 2x. What's the slope on each of these? 2. It's just the coefficient, it's not the variable. So the slope for both of these lines, slopes are equal. The slope for both of these lines is the ratio or the rate 2 to 1. That's the slope, 2. We use the little letter m. And the only difference between them is one of these lines says if I just take my x value, the same x value for each, one of them, the output value is 4 greater. I just take wherever I am on my y value for my first, the black line, and I just move up 4 units. It's been the entire line. It literally means that I could pick this line up and literally shift it up 4 units, and I'd be with my equation y2. Okay. How do you know if I gave you these two equations and not the table, how would you know that the green one was y2 and that the black line was y1? What else tells you that? That the green line goes with y2 and the black line goes with y1. What else tells you that? Has bigger numbers where? All right, no table, just the graph. Yep. The y-intercepts, right. Remember, your y-intercept is when x is 0. So when x is 0 here, y is 0. When x is 0 here, that constant always tells you. If I wrote y1 like this, y1 equals 2x plus 0, it's the constant that tells us the y value, the place on the y-axis where my line crosses it or intercepts it. Okay. So let's take a look at 3. Before I ask you what equations your table came up with, let's take a look at it. And again, this language is important. What is the y-coordinate when the x-coordinate is 2? Well, most of us know that we go to the right 2 units and we go up to see where we intersect. Or in other words, if we dropped a vertical line straight down through x equals 2, we're looking for the intersection of that vertical line with our graph. It happens at 3. So the point 2, 3 is located on that graph. What are the x coordinates? Note, x coordinates. So we're going to have 2 answers to this question. What are the x coordinates when the y coordinate is 4? So what could I do visually to help me get the answers to that? What could I do to my graph to help me answer this? Someone over here who hasn't participated today? What could I do to that graph to help me answer that? Table 1. Yeah, at y equals 4, I could draw a horizontal line. All right, and if I did that, if I drew a horizontal line, and I'll try to draw this straight. Oh, I'm doing pretty. There we go. All right. So if I draw a horizontal line straight through y is 4, so the equation of that line is exactly what I just said, y is 4, then I notice it hits my graph in 2 spots. So those 2 spots are -3, 4 and 3, 4. Okay, so -3, 4 and 3, 4 are points on the graph. Okay, this question C and D, we're going to be learning the names for each of these sets today, and we're going to be using these names over and over, but I want you to see that you can answer the questions without the names. So it says use interval notation. So first you got to dig back. What does interval notation look like? To describe the set, so it's a set of numbers that contains all x coordinates of the points on the graph. So the x-axis here goes from -6 to +6, right? But in reality, how far does this extend? Infinitely, because notice this graph continues in the direction of positive infinity and negative infinity and positive, to positive infinity. The lines are going straight up. They're never going to stop. So there's no limit on the values of x that you can put in there. So it's actually this entire line, the entire x-axis, this entire real number line would be how you would describe all possible x values that you could use as input into this function. Oops, can't use the word function yet. All right, so interval notation, how do we say all real numbers? That's a fancy way to say real numbers, right? The set of real numbers. It's like an R with a double stem that represents a set of all real numbers. So in interval notation, what I saw you do is negative infinity to infinity. Some of you had this reverse. Please make yourself a little note that with our interval notation, it's the smaller number to the left and the larger number to the right. Even though these aren't numbers, they represent two ideas, two concepts, where negative infinity is to the left of positive infinity. Cornelia? Yeah, because brackets actually mean that it's a specific number or an endpoint, and there is no like number that represents infinity. Because you give me a number that you think might be infinity, all I have to do is add 0.1 to it, and I've got something bigger, or vice versa, something smaller. So we can't include infinity and negative infinity, only specific numbers in our intervals. Okay, now I want to just come up here and erase everything that I've done here really quickly. So the green line. Now it says use interval notation to describe the set that contains all y coordinates of the graph. So literally, if you went to each point here, every single point, and you came back to the y axis like this, if you just drew right here from my line right over, and you started including the point you started at, the y value you started at, what would be the smallest value that my y coordinates can take on? What's the minimum number for my y value? 1, right? Here it is. Every other x that goes into this equation for this graph makes y bigger than 1. So now, because 1 is part of these values and it's a specific number, I can use the bracket 1, 2, and what else do I use to complete this interval? Infinity, right, with the parentheses. Okay, so I asked some of you to come up with what might be an equation for this. Danielle? No, because you're using this to describe all y coordinates. This isn't always x. It depends on what you're answering. So this is the answer to the set for all x coordinates. This is the answer for the set to all y coordinates. Earlier, when we were talking about interval notation, we were just using the real number line because we only had one dimension, and that was when we were talking about x's. But now we have two dimensions. We have both the x coordinates and the y coordinates. So you can still use the interval notation to represent sets regardless of what the variable is. Later on, we're going to have a name for these that you'll put in front, so you'll be clear about whether it's like the variable along this axis or the variable along this axis. I just can't give you the name just yet, okay? So some of you came up with two equations for this. Some of you wrote this, and some of you wrote this. Those of you who wrote this and only checked the positive values of x thought you were right. You said, oh, if I put 2 in for x, I get 2 plus 1 is 3. I'm at 3. That works. And this is because of the reason about absolute value being two possible numbers inside, both opposite numbers. If you try something on the other side, like -2, and you put it in here, you get -2 plus 1 is what? -1. Absolute value of -1 is 1. Oh, that's not equal to 3. So sure, if you just think about erasing the left side of this absolute value, the line x plus 1 notice this part of x plus 1 isn't included. So on your test, when you solve absolute value questions and you just kind of remove those parentheses, those absolute value bars, or if there was a number out there and you distribute, you're going to get half of your answer right. Because half of this function, or the right side of this function, acts just like the line x plus 1, but only for the numbers 0 to infinity. The second part of this function acts like if I extended this line this way, or extended that line, that ray this way, what would be the slope of this line? What would be the slope of this line, positive or negative? Negative, right? And remember we said absolute value has two different answers, right? Positive and negative could be inside of the absolute value, a positive number or a negative. So it doesn't work just to say x plus 1. When I asked you to check it, you saw that that wasn't correct. Some of you had this answer. And if you recognize that the absolute value graph, without anything funny happening to it, just based on its definition, y equals the absolute value of x, which equals x, a line with slope 1 when x is greater than or equal to 0, or part of the line for that domain. And the opposite of x when x is less than 0 means it's got to have a negative slope for that ray right there. So this is the absolute value of x. That's why you need two equations to define it, because it is represented by these two pieces. We call this a piecewise function later on. All right. Now, if you just compare the y values between the green graph and the blue graph, it's just been moved up one. All the y values, here's your y value for your absolute value function, the green function, and then you've just added one to all of the outputs to get your blue graph. In other words, I could literally take this green graph and move it up one, every single y value up one, and now I'm on the blue graph. So this is what we call transformations, and we'll be doing this starting next Friday. Okay, I want to give those of you, I think most of you have had great attendance, but I just want to point out that starting next Friday, October 7th, and then notice we have Monday off. If you're thinking about taking a long weekend, an extra long weekend, I would really discourage you, because do you see transformation of functions as an entire week of class time, which means this is pretty critical, and it gets very complicated. It starts off okay, and then it can get really complicated. So you do not want to miss one of these classes if you can absolutely help yourself. Okay, you really want to be here for those classes. So if you're thinking, Wednesday I go to class and I won't have to return for a week, I maybe go on a little vacay or whatever, think about it, because as you can see, anytime we spend 3 classes on one concept, that means it's pretty important. Okay, again, you make your own decisions. It's your life. I just want to point that out to you. Okay. So we're going to start off with the demo with this idea called relations, and let's see, who wants to talk about relations? Read that for us. Okay, thank you, Ben T. Yep. Okay, so if we're going to write a set of ordered pairs, notice this begins with the curly braces. They're ordered pairs, which means you have 2 components. You have a first component, in this case is the name of the Celtic player, separated from its height with a comma. So you have 4 ordered pairs. The first component in each ordered pair isn't an X value, it's a name. And the second component is a quantitative measurement. It's the height of the person, 6 feet 9 inches, 6 feet 2 inches, 5 feet 9 inches. Okay. The set of ordered pairs above is called a relation in mathematics. It's just called a relation. And the definition for a relation is a set of ordered pairs. Very uninteresting in a way. And, you know, any set of ordered pairs, you don't have to have any special conditions on it. It just satisfies a relation. Set of ordered pairs. Okay, that's called a relation. No problem. Let's see what happens if we wanted to. Oh, let me just finish this. The set of names, again, notice set of names has curly braces. David Lee, comma, Avery Bradley, Jared Solinger, and Isaiah Thomas are what we call the first components or inputs. That's the language we use. It's the input of the ordered pairs or the first components of the ordered pairs. Anytime you're looking at just the inputs, this is what we call the domain. Now, we've had domain earlier when we were looking at rational expressions and we were looking at what numbers were okay to have the fraction have meaning, and we excluded certain values. That's where we first saw domain in this course. Now we're looking at domain as it applies to these sets of ordered pairs, and any of the first components, or each of the first components, is what we call the domain. In this case, it's the domain of the relation, because that's what we're looking at. If I go back to our preview activities, answer at your seats with your group. Which of these questions in part 3 here, C or D, represents the domain for that graph? Answer that at your seats. Which of those two questions represent the domain of this particular graph? Okay, so what did you come up with, C or D, for representing the domain for that particular graph? C, because we're looking at the set. So in this case, the set is described by interval notation because we don't have finite elements. And it's all the possible inputs, which we were used to calling our X values in the ordered pair. So this is actually called the domain. Whatever your input is, yes. It may not be X if we're looking at, say, distance versus time, right? It depends on what your input variable is. Yes, yes. Input is whatever's on the right side for the Y equals, yes. All right, let's take a look at the next thing. The set of heights, again, these 4 heights, notice I didn't duplicate 6 feet 9 inches, just like when we were talking about the Beatles reunion. When we look at the union of sets, we don't duplicate if a person belongs to both sets or a number belongs to both sets. We only list it once. So very similar to class 2 when we were talking about unions of sets. The set of heights, 6 feet 9 inches, 6 feet 2 inches, and 5 feet 9 inches, is the set of second components, or what we're going to call outputs of the ordered pairs, and it's called the range of the relation. Okay, so that means that back here in question 3, this set of Y coordinates is what we would call the range for this graph. So this is called the range. Okay. Okay, so let's play a little bit with this now. So if we represented the domain and range with these Venn diagrams, the domain, we would list each of the first components that we have in our domain on the left side, and on the range on the right side would have 3 elements because we have a height that's repeated, so we only list it once. And then we would draw this correspondence that we were talking about, that for each person on the Celtics, each of these 4 players, the player's name goes to one and only one height. That goes back to Victor's question in the preview activities when he asked about this language. So now it would be each name of the Boston Celtics is paired with only one height. So we see that here by this line only going to one height. In the ordered pairs above, we listed the name of the Celtic player first and their height second. However, what if we switched that around? What if we created another relation by listing the heights first and then the name second? There's no rule saying we can't list the height first in the name section. So let's fill out this domain and range for this particular relation, because a relation, remember, is just a set of ordered pairs. So what would I fill in the dark blue Venn diagram? What would I put in there? Someone want to help me? Yeah, and what would it look like? I'll put a little dot like this. 5 foot 9 inches, yeah. 6 feet 2 inches, yeah. And 6'9". Right. And what would I put in the range over here? Someone want to help me with that? Yep. Yep, their names. So let's just use the first name. David, Avery, Isaiah. Any Boston Celtics fans in here? No? I was going to say which of any of these players not on this year's team. Anyway, but all right, so if we show the correspondence, 5'9" would go to which name? 5'9" would go to which name? Isaiah, so that would go here. 6'2" would go to Avery. And 6'9" goes David and Jared. So if we look back at the preview question, I'm going to take that language again since it was a little confusing. In which set is the x coordinate paired with only one y coordinate? We don't have x and y here, but do you see here that an element in the domain that 6 feet 9 inches is not paired with just one Celtic player? Okay. All right, so now let's play a little game. Suppose last year the Celtics won the NBA championship, which we know they didn't, but we'll just play. And I've been handed the MVP, which stands for the most valuable player award. And I walk into the locker room to hand it and all to the player who won the MVP. But all I know about the player is that they're 6'9". Who would get the award? Neither one of them?
Either.
Oh, either. But I can't, like, I mean, I need to know who to give it to. Who do I give it to? Nobody. I'm kind of out of luck here, aren't I, right? Because all I know is if they said the player was 6 feet 2 inches, do I know who to give it to?
Oh, yeah.
Yeah, it's clear, right? It's really well defined. I clearly know who to give it to. Or if they said 5 feet 9 inches, it's Isaiah, right? I have no idea. So this is a problem, Houston, right? That might be going beyond your age. When you remember Apollo? Oh, okay, you got it. Okay. So let's take a look at the next thing. We are now going to define the concept that's critical to the rest of the course called functions. So you want to read this for us, Molly? Without going back to our basketball example right now, but we go back to our preview activities. And we go back to these activities and we look at this blue graph here. I'm going to remove the green graph, which is absolute value. If we look at that blue graph, is there exactly one output value for each input? I hear a yes, 2 yeses really quick. Is there exactly one output value for each input?
Yes.
Yeah. How could you see that visually? With a vertical line. A vertical line is a way of taking all of that language and having a real quick visual test for that language. For each input, so I pick any input, I can only have one output. So if I literally move right from that x coordinate up and down a vertical line, and that vertical line hits that graph in one spot, I am a function because I only have one output value, one y coordinate for that given x value, or the input value, whatever the variable is. Okay, so that you'll see later on in your class activities, but try to match the language with the test. Okay, try to match the language with the test. All right, so in our basketball example, at your seats, decide which set of ordered pairs represents a function and which set of ordered pairs represents a relation. So at your seats, write that down, and when you have consensus, put up your flag. So given that there's total consensus in this classroom, everybody answered this question exactly the same, it must be correct, right?
Should be. On that example.
Hopefully, okay, should be, hopefully. What if I tell you it's not correct? Iris says, you know it's correct. Okay, well, Iris like saying he knows it's correct. I'm telling you it's not entirely correct. I agree with which one of those sets is a function. I totally agree with that. So I've alleviated half of the anxiety, all right? I absolutely say, let's see if I can find the creative pen. Oh yeah, here we go. I absolutely agree with that one. P is definitely a function. For each player, there's one and only one height given as a second component. I do not agree with the relation that you've listed. Which set or sets of ordered pair is a relation? How do you get to be a relation? You're any set of ordered pairs. How many sets of ordered pairs do you have there? Two, right? H and P. So you always got to be a little careful. This is H and P, H and P. So this is like, okay, H and P. Both H and P are relations, but to be a function, you have to be a special relation. Okay, and only one of those is the special relation that for each input, there's one and only one output. Okay. Okay, so what else do I want to say about this? I think that's enough. Okay, let's now take a look at functional notation. Some of this may be old hat to some of you, so bear with me. For some of you, it may be very new. So I'm going to approach it as if you've never seen it before. There's lots of ways to represent functions. Sometimes we can represent functions with tables. You saw the representation of functions with the set of ordered pairs. You can also represent functions with equations and with graphs. Okay, so right now we're looking at the relationship between time and height, the time that a baseball's been in the air and in seconds and its height above the ground in feet. That's a relationship between two variables. Okay, and the relationship is given in this table. So which of those rows, the height row or the time row, is the domain? Time is domain because it's the set of input values, and height is the range. And I only know that because of this line that says in the table above, we define a function and we say y, the heights, is a function of the time. That's why I knew what the input was the time. Once I know the time, I can tell you what the height is. Instead of using the variable y to represent a function, we use letters such as little f, little g, little h, big F, big G, big H. We can use other letters. These are the letters commonly used to represent functions. And this idea right here is an important one to make sure that you understand. Let me get my pen out. I don't want my creative pen, just my regular pen. Okay. Y equals f of x. This is the notation for that language right there. Y is replaced with the equal sign. Function of x is replaced with that symbol f parentheses x. F parentheses x does not mean what you first learned when you first started algebra. It does not mean f times x. They are not factors. It's a notation that says y is a function of x. That's how we read it. Okay. Now, how could I now write this with our function notation? How could I now write this with our function notation? What would it look like? What would that ordered pair look like? I want to write x, the input value and the output value. Ben? F and f of x. X and f of x. All right, Ian. X and f of x. Okay, if I messed up, I apologize. X and f of x. Because y is the same as f of x. Okay? Okay, so when you see this notation f of x, the x is always your input. The entire thing, f of input or f of x, the entire thing is equal to the output. For this particular function, the input is in seconds and the output is in feet. Let's take a look at how we evaluate and interpret functional notation. So everything's going to relate back to this. Now, when I did domain and range here, I knew that because secretly I saw y and x here. And I knew that this relationship would be described in terms of x. But it could have been reversed. But this is just the way it is for now, all right? Maybe it could have been reversed. I don't know. We'd have to look at that a little more deeply later. All right. So evaluate each expression using the table values for the height of the baseball as a function of the time. So when you see f of 2, the first thing you say to yourself is my input is 2 seconds. What is the corresponding value for the output? And you go up to the table and you see that it's 99. So what you're used to writing like this, 2 comma 99, could be replaced with 2f of 2. Both of these are exactly the same because f of 2 is exactly the same thing as the number 99 according to that table. All right. So f of 2 equals the number 99. It's asking us, this question is asking us to find the output value, the height of the baseball in feet, when the time is 2 seconds. So how do I interpret this? Just like on the test, just like on the project, just like on the quiz. Every time you interpret coordinates, both of the numbers that you see in the coordinates and their units must be present in your explanation or interpretation. Does anybody want to try the interpretation of this? Nobody? I don't believe it. Come on. Yeah, it's just a sentence. Okay, you went too fast. What? 2 seconds, yeah. After the ball, baseball, I think it's hit here. It's hit, yep, hit. Yeah, I think we hit the baseball, but it doesn't matter. Okay, go ahead. Is 99 feet. Okay, good. Okay. Look at what we start with. What are we given here? Input value or output value? We're given the input value. We're given the input. So guess what? That's how we start our sentence. We start the sentence with 2 seconds because that's what we're given. F of 0, we go to t, x equals 0, the height is 3. So what's the value for f of 0? 3. It's the output value when x is 0. So to interpret this, what might you say? Someone try this one? Yep, Ian? Okay, when the ball hits the baseball bat, the height is 3 feet. I agree, but guess what? I've just agreed to something that I literally said a moment ago isn't there. You do not see the number 0 there. But how is 0 implied, 0 seconds? How is it implied in that sentence? Eric? Which is what phrase here? When the ball hits the baseball bat. Often in mathematics and science, when your initial time is 0, we say initially. Initially, the height of the baseball is 3 feet. And it's that word initially that means my x value in this case is 0 seconds. So often we'll use the word initially Ian happened to use the phrase when the ball hits the baseball bat. Okay. Yep. Victor?
You could also say 0 seconds.
Yes, you could be very literal and say, just like you did before, 0. You can use the same sentence from above. 0 seconds after, blah, 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 the height is 3 feet, right? Look at C. What are we given in C? Input or output? We're given the output. We're given the output, which is 103 feet. So our sentence begins with 103 feet. When the baseball is 103 feet above the ground, the time would be what? At what would the value of the time be? 2.5 seconds. You go up here and now you focus on your output of 103 right here. 103 happens at 2.5 seconds. Okay. Have fun with your class activities. So really for this sentence to be a little better grammatically, we could just say the baseball is 103 feet above the ground at or when the time is 2.5 seconds. Okay. But that's a little bit better than starting with the when.